All right, so welcome to another video. We're going to be taking a look at some more advent of code today. I didn't make a video for yesterday's problem 7, but I was able to finish it. It just Mondays I teach all morning, so by the time I got up and I'll talk about the problem a little bit, but I got up and I was trying to get the first part done either before my first classes and then in between my classes, but I just had a problem I couldn't figure out. It turned out that I was not parsing the input quite correctly, and then once I fixed that, everything worked, and then I was able to finish part 2, but I just did not have the time to also put together a video or a post on it, but today's one went a little bit smoother, so we're going to take a look at both of them. I'm not going to code up a solution to problem 7. We'll just look at a few of the aspects of my solution, for better or for worse, and then we'll code up a solution for day 8. There's some interesting things there. So problem 7 was interesting in that we had these, this description. So again, we had this this parsing. The problem was how many items I would take out of the list when I parsed it. But anyway, that's not a problem. But anyway, so we have this relationship. So the light red bags contain other bags. Let me actually bring this up. So this is the problem. So the light red bag contains 1 white bag, 2 yellow bags, etc. So bags contain other bags. And so what this sounds to me, it sounds kind of like a graph, a relationship. The idea that you'll have like a light red bag contains a bright white bag, and just moving my windows around so I can see my screen, and it also goes to a muted yellow bag. And then the second line of the input happens to say a dark orange bag contains bright white bags and muted yellow bags, etc. So this sounds like a graph type relationship, but it's asking, the question is asking, how many bag colors can eventually contain a shiny gold bag. And so if you look at the data setup, basically you'll be able to have a bunch of bags and you can follow them. They will contain something, will contain something, will contain something, and eventually that will get to the bag you're looking for, the shiny gold bag, but multiples of them might get to them. You'll have the situation where one bag can get to another, to a yellow bag, etc. But if you look at it in the reverse, if you make it backwards, so instead of saying, and I'll talk about this more in my blog post that I'll write about this, not how many bags, this bag contains another bag, you can go in reverse. You can say, I start with a yellow bag. I can be contained in. So if you go in reverse, go from the shiny bag out, then it just becomes kind of a tree traversal, graph traversal, type problem to see how many nodes can you get to from the shiny gold bag. So let's look at the code that I did for this. I have to get to my cursor to the right place. And this is day 7. And so I'm going to do a cider jackn. And a big part of this was indeed the parsing. So once this comes up, we will change our namespace to day 7. And so we'll just go, I'll just evaluate the whole buffer just because, just to make sure that everything is executed. But at the course of this, what I'm going to do is I'm going to parse a line. And so the line is going to, each line of my input, I'm going to take that string, and then I'm going to break it out into my list, where I get like color count, color count, color count. Well, actually, let me just go to the beginning of it. We'll do it a step at a time. So the first thing we're going to do here is we're going to make our data. These are our raw data. And our raw data is our usual. Let's just actually run this. And if we look at our raw data, It's just our lines from the text input file. So light red bags contain 1 bright white bag, 2 muted yellow bags. Then the next line, dark orange bags contain, etc. So then I'm going to filter my data. What I'm going to do is I'm going to pull out no other bags because there were a few lines that had no other bags and those didn't seem relevant. It turns out that this didn't make a difference for part 1, but for part 2 it did. So I'm going to pull those out. That's my data. And then I'm going to parse all of the lines, and that's going to give me a data list. So if you look at this, this gives me a line. So this here, this says, actually if I look, it's going to be a list with a first item, so the light red bag can be gotten to. So this reverses the edges, bright white and muted yellow. And in fact, if we look here, the shiny gold bag, it is directly connected to by the vibrant plum and the dark orange. And if we go back to here and we look for our shiny gold bag, well, actually, I'm looking at the wrong place there. The shiny gold bag is in the bright white. And the shiny gold bag, is it in any other one? Oh, and in the muted yellow. So coming back to here, oh, I haven't made my graph yet. So I'm going to parse the lines, and then I'm going to add them to the graph. And so let's go and look at those routines again. So parsing the line, and you can look at all this on GitHub. Parsing the line, I'm just splitting this on the word contain. Let me go back to the Emacs window. I'm splitting on the word contains, which means you're going to have a left-hand side A and a right-hand side B. And the left-hand side, I'm just going to basically turn it into a keyword. I'm going to take the first 2 words. So it's going to be like light red is going to become light red, just one word, and I'm going to turn it into a keyword, and that's going to be used in my, as a key in my graph. And then the right-hand side, I have to parse the right-hand side. And parsing the right-hand side is basically going to convert those into these color count combinations. And then that calls make color count, which does that, etc. And then finally, I can add these to my graph. And so I'm going to add these, each one is going to be added to a graph. And so at the end of this, if we look at our graph, I made graph part 1. Notice here that my shiny gold, there, let's do it down here. My shiny gold bag goes to muted yellow and bright white. Just from here, if I look at muted yellow, it has a shiny gold bag, and a bright white has a shiny gold bag. So this graph represents the nodes, but in reverse. Okay, but basically, so if I now start here and I go shiny gold goes to muted yellow and bright white. Then muted yellow goes to dark orange and light red. And dark orange goes nowhere, so that's not in here, there's nothing more. And so that's it for that traversal. And to do that, I just did a basic search. And I have that under BFS1. So it's a basic search, and I did this, and again, you can look at the code for it. I did this using the loop construct, essentially. Basically, I have, I just make a frontier, which is my list of items. I think I'm using it like a stack, but I might not be. It depends on how the conjoin works if you dig down into this code. But it does either a breadth first or a depth first search of this until it visited all the nodes. And then when it's done, it basically has the list of all the things the yellow can give me. So you can look at the code here, but it's basically just a search. Now, a couple of things about having written this. I thought that, reversing the edges made a lot of sense because then it's just a search and that's an algorithm that I know I can code up, etc. But I just suspected that we were going to need the counts, like how many ways you can do it for part 2. So I kept those. And it turned out that made my life a little bit harder because, it's always easier to deal with I could have just dealt with like if we look at the, I didn't show the code for a lot of this, but it's okay because this is just on GitHub, and yeah, I really have to remember to change Windows. Sorry about that. But you'll see here, this would have been easier if I didn't keep like shiny gold, muted yellow 2. I don't use that 2, but I thought I would need it in part 2 later on. And, you know, and it didn't. And as it turned out, it just made it a little bit more cumbersome to parse and create. But anyway, that was part 1. Part 2 was very similar, but now all of a sudden it was going forward. You know, like the question says, how many bags are required inside your shiny gold bag? And so I kind of had to do a forward search instead on this. So like here, my graph looks like this, but my graph for part 2 looks like this. It's the reverse. If we look at the original, thing, it says that the shiny gold bag goes to dark olive and vibrant plum. So it's like the direct graph. So actually the code to create that is a little bit easier. And then for this one, I just did again, so you can look at the code later on, I did a true recursive search here, but what I did is at each level of the search, of the recursive search, what I did is I basically added up for each of the neighbors in a given node, I multiplied how many times that bag could appear with all the stuff inside it, with the recursive call inside it, and that's this line here. So anyway, this was pretty, the code, once I got rid of my mistake, was pretty straightforward. It was just a breadth first search problem. But this one was also interesting because if you don't know those data structures, this is a lot more of a bear. So like for part 2, if you knew the data structure, if you knew the algorithm, breadth first search, and you knew how to build a graph, an adjacency matrix, not an adjacency matrix, an adjacency list like this, it's pretty straightforward. And the first part is pretty straightforward if you see that insight that you can reverse the edges instead of going forward, go in the other direction. But if you don't, this becomes a lot harder. So this is kind of where having that data structures background and that algorithms background can certainly help. So anyway, that was problem 7. So let's look at problem 8. So let's go back to here, let's go back to here, and let's go back to here. All right, so here, this problem deals with a little simulator. You're basically simulating a very small machine. It has 3 operations, a no-op, an accumulator, and a jump. And that's pretty much it. And you have to run it through, and basically you have to kind of run this simulation, keep running the problem, you know, your program. So you start here, it won't do anything, and then it comes over to here. Then it adds one to the accumulator, and then it goes to here. Then jump +4 will go from here down to here because it just changes the instruction pointer. Then it'll go to here, etc. And you want to keep doing this until you get back to your original point. So let's take a look at this. So let me get to here. And we can start. So we'll do our usual. Our data is going to be, we're going to read sample 08.dat and just make sure your files are right. And then we're going to do to IO resource and slurp. So that's good. And then we're going to do our string split lines. All right. So basically, now we have our lines, you know, 1 per line. And then what we're going to do is we're going to want to split this up into our actual command. So let's define Parseline. And let's do with Parseline, use destructuring, opcode, and the param string will just be Yeah. All right. So basically, we're going to destructure this. We're going to split the command, which is going to have those two pieces on it. The first part's going to be the opcode. The second part's going to be the parameter string. And then we're just going to put into this, or we're going to return, let's return the keyword based on the opcode, because we'll turn that into keyword to make it easier to deal with for indexing purposes. And then we're going to do u-parseInt, which is the little utility function that I wrote for utilities, of the parameter string. Return that. That's the let, that's the that. And then we could say Parseline, the first of data. And we got a mistake there. That's data. And so let's see, what's our problem with Parseline? First data. Get that error again. Oh, I forgot. Yeah, I messed this up. I messed that up, but I didn't mess that other part up. Okay, so now it splits it up to a no op and a 0. And if I did map Parseline on the data, it just converts all of them, which is nice. The thing is, when I was thinking about this, I was like, you know, I don't know if I'm going to need this, but we have to keep moving up in different lines. And so why don't I actually add another parameter here for my line, and I'll put this first in as a line number, and then I can define my program, and my program can be, or actually let's just do, and we'll take our data to our program, we'll take our data, and then what we're going to do is we're going to return map indexed Parseline on my data. There we go. So we can say data to program of my data. And that should be okay. Oh, Parseline is, no, Parseline takes two things. Or do I have to re-execute that? Yes. Yeah. Okay, let me. Data to program. I'm not thinking on all cylinders here. Still not spelling right. There we go. Okay, so that was a whole lot of stupid in a very short period of time. So anyway, now the thing is that I also might want to get specific items into this. So let's actually return this as a vector so I can use the nth option to get this. So now we've got our data, we've got our program, that's all pretty good. So what we have to do is we have to simulate this. So fortunately, if we have a program we want to simulate, we're going to have a state for the machine. So we're going to define a state, and the state is going to have an instructional pointer and an accumulator. So just that's what our machine is. And as we run through our program, we're going to modify these. And we also have these operations that do things. So I'm going to write them like this. So this is going to be how I will do a no-op. So for example, if I do a no-op off of, and my parameter will be, it doesn't matter what parameter is, and this is my state, which has 0. Now my instruction pointer is 1 because the no-op just goes to the next instruction pointer. Then my next one is going to be jump. And for jump, what I'm going to do is I'm going to add whatever the parameter is. So if my jump is my instruction, and I'm going to add 3 to the state, my instruction pointer goes to 3. And then the final one is the accumulator. And for this one, we just got to do a couple of things. So we're going to use a threading macro here. So we'll start with the state. And the first thing we're going to do is we're going to update the instruction pointer by incrementing it. And then we're going to update the accumulator by adding whatever the value is to it. So now if I do an accumulator by 3, the instruction pointer gets added one. In each of these, it's the original instruction pointer, and it's also modified the accumulator. So those are my options. Now, you might wonder, why am I writing them in the exact same form? That's because I'm going to have to simulate this. And if I would simulate this like in old school when I was first learning and have a bunch of if statements. But what you can do in a lot of modern languages is you can do something like this. So we're going to make an ops dictionary. So the accumulator is going to refer to the do accumulator. The no-op is going to refer to do no-op. And the jump is going to refer to do jump. And so those are my ops. So what this lets me do is if I say, give me the jump from ops, it returns a function. So I can call that function, and that function is going to take a parameter and a state and run it. So now I can use this to directly run my function. So this is all my setup. And now finally, we can run our simulation. So to do this, we're going to run a program in a state, and we're going to run a loop. And the loop is going to start with the state as being state. And we're also going to pass something called visited, which will start with just an empty thing, an empty list, an empty dictionary. We're going to use that to keep track of when we hit a second thing twice. So now we have our condition. So depending on the situation, if if we're not visited, or if we have not, or other, if it's not nil, so we have visited the states. As we visit our states, as we visit our lines, not our states, as we visit our lines, we're going to put them into that visited dictionary. So if it's not nil, if we have visited it, it's not going to be nil. We just want to return the state because we're done. Now, that's the first thing. The next thing, though, is otherwise, we're going to make a few values for convenience. We'll get the instruction pointer. And we're going to get the line number, the op, and the param from our program. Since the instruction pointer is going to be what line we're at, we're going to pull out from it that instruction, because that's the instruction we want to do. Our new state is going to be, we're going to run the op on the ops. So it's going to do that lookup. So it's going to run one of those 3 ops. And we're going to run it on our parameter. And we're going to run it on our old state. And our new visited is going to be, we're going to just set that we visited this instruction pointer. We're going to turn that to true. All right, so that's pretty much it. And now we set up our variables, so now we can do our recursion, our loop. New state, new visited. And we hope that's it. So now we can run our program on our program state, and we're unable to, didn't we define program? Oh, we actually didn't define program. Let's do that down here. Def program to be, and now we run our program, and it turns out our accumulator is 5, which is what our answer is supposed to be, and there, that was that. So that was pretty straightforward, and if we ran this again on the day 8 input to make sure it runs on that. So we have our data, redefine our program. Our program is indeed much bigger now, and 1949 is our value. That was the value that my data was supposed to get, and that's part 1. So that's pretty much it. Now, the nice things here, let me just change the sample. The nice thing here is that ops thing for the simulator makes it nice and easy. And so this was a reasonably straightforward simulation, and now we get to part 2. And so for part 2, it's basically saying there's a mistake. And the mistake is, the problem with the mistake is once we get to, it's not that our program's supposed to crash like this, so it's supposed to get into this infinite loop, this repeating state. It's supposed to end, but one of the instructions, either a no-op is supposed to be a jump, or a jump is supposed to be a no-op. And so we have to figure out which one it is, and then figure out what our output is really supposed to be. So that's an interesting problem. So what I thought I would do is we can run our program, but what we're going to do is we're going to run our program, and it turns out we're just going to change the, well, actually we're not going to change this. We're going to make a copy of this. And we're going to call this test program. And here, what we're going to say is if this is an endless loop, like if it goes back to a visited, it's going to return false. But on the other hand, we're going to say if our IP is the same as the number of lines of the program, so this means it just went past the end, because remember the IP is going to be a state from 0 to 1 less than the number of lines in the program, then we're going to return true. So what this will do for us for now is this will return true if our program actually finishes. All right, and actually, rather than that, let's just actually return our state if the program finishes. So now, let's run did I not run that? Unbalanced paren, so let's fix this. That should do it. Test program, program state, and that's false because that version is false. The program as is has a problem. But what we want to do is we want to now try all of the problems, all the programs we can do, all of the candidates where we might change a no-op into a jump. So let's do that. Our no-op candidates is, well, we're going to have to convert our candidates. So let's actually write a routine. The idea there is if we have a candidate, we want to switch no-op to jump or jump to no-op. So we're going to write a routine convert candidates, program from to. We'll take our program, and what we're going to do, we're going to filter we're going to pull out all of the lines that have the from that we're looking for. So let's just do that first. So if we say convert, let's look, did I load my smaller program again? Yes. So if we say convert candidates in my program from a no-op to a jump, that's the only one. That's the one line. I have to change the 0th line from no-op to jump. But if I want to change from jump to no-op, those are the ones. I have to change command 2, 4, and 7. So we're going to first filter. We're going to get those lines then, and then we have to do the change. So we're going to then say map function. So for that line, we're going to decompose that line into its ABC components. And we're going to return A, but instead of B, the command, from is going to become 2, and then C. So here, these are going to pull out all those jump candidates and change them to no-ops. So that should be our next step. So now, we're going to now say, our no-op candidates are going to be convert our candidates in our program from no-op to jump. And then our jump candidates are going to go from jump to no-op. So those are going to be the ones that we have to do our switch for. So now the next thing though is we want to change our program. So for each of these, so for example, if we look down here, we want to first change our program so instruction 2 becomes this, and then see if it runs. Then to see if instruction 4 becomes this, and then see if it runs, etc. So we're going to need another routine that's going to be helpful here. Swap instruction. We're going to get a program, and then we're going to take into it an instruction, but I'm going to decompose it into its 3 component parts. So for example, we're going to pass into this to no-op 4, and what it's going to essentially do is it's going to swap out the old instructions. So we're going to associate in our program the line number is going to be the line number op param. And I think there's a way of doing the destructuring so I can also get the whole thing, but I forget what it is. Got to spell program right. So now if we look at our program, and if we look at our jump candidates, so that's if I say swap instruction from our program, let's say our first of jump candidates, that's going to change. Right now, line number 2 in this program is going to be a jump, and now line number 2, as we can see, is a no-op. So now we're almost done with our program, with our part 2. So for our part 2, what we're going to say here is, let's, how should we do this? Let's see what this does. So we're going to filter, and the function is going to run test program on swap instruction program of S. So it's going to do that along with the initial state for our no-op candidates. And we got a problem here, which as usual, I can't spell. There we go. And none of those fit the bill. But on the other hand, if I try my jump candidates, there we have it. We basically have that one works, and it gives us 7 and -4. And is that the right answer? Do we have to calculate something? I'm looking back. And I think that's the right answer of what we get for that. Yeah, so that's pretty much it. So let's change this to day 8. Get our program. And let's make our candidates, and make our jump candidates. And that is not quite the right answer. And I think that's not the right answer because we have to actually, what do we have to do with this? Oh, right, because, so anyway, but we do see it is, that's not the answer because 174 is the accumulator at the state in question. That is the one command that now, if I switch it, will be correct. So what I actually have to do is I have to let's see. It's got to be 265 no op -174. Okay, so if I look at this new program now, 265, whatever that was. Well, actually, let's scroll back. This now is a no-op when it used to be a jump before. That's our new program. And so now, let me just see what happens if we run our test program on new program with state. And we get our answer of 2092, which is actually what we're looking for. So that's a solution to this problem. And I like this, I like this filtering out to get our candidates and stuff like that. There's a lot of good stuff going on here. But that's problem 8 with a little bit of problem 7. I've rambled on for over a half hour, so I think that's enough, but I hope some of you enjoy this.